Hello everyone. Thanks for joining the Connect session. So as you know, this is an opportunity for the community members to come together um, and exchange the research results amongst us. I wish to keep this like a small, close-knit event where we kind of get to know each other also at a personal level. So that's kind of the philosophy behind this, like having a reading group with authors presenting the work by themselves. So today we have two speakers, Ankit and Mengting. I think Mengting is the first speaker, and then Ankit. So you know how it works. So you introduce each other. So please, yeah, you may start at any point you like.
Let me just first share my slides to make it can you see my screen?
Yes.
Okay.
All right, so I think I'm gonna introduce Mengting first before the presentation. So hello everyone. So for our first talk, we have Mengting Ai. I'm sorry if I'm pronouncing it wrong. Please correct me afterwards. So
Yeah. Hold on. I think it's a little bit janky. Let me sorry.
Don't worry. Take your time.
Yeah.
You have some time.
Yeah.
all right, so yeah, the first talk is from Mengting Ai, who's a PhD student at the School of Information Sciences at the University of Illinois, Urbana-Champaign. And this talk is going to be about some structured pruning method for compressing large language models. And I see that the method is called NIRVANA. And yeah, I'm excited to learn more about it. So yeah, over to you, Mengting.
All right. Thank you, Ankit. So today this topic is about NIRVANA, which we propose as a structure pruning method for LM compression. And I'll be talking like this talk will be outlined as the follows. So I'll start with the motivation. So in general, LMs are typically too large for deployment. For example, a 7 billion models requires approximately 14 gigabytes at flow point 16. That result in high inference or training cost. Some other work in the pruning field includes unstructured pruning, which they typically like remove weights from the model, but that cannot really provide some hardware speed up because the sparsity pattern of unstructured pruning is irregularized. So take a step further for semi-structured pruning, because they have the pattern, say like among four weights, two of them are set to 0. This enables some NVIDIA techniques like to actually provide the inference speed up, but those cannot be really translated into the fine-tuning process because that pattern could be broke during the process. And then for one-shot structure pruning, it's considerably harder than semi-structured and unstructured because first, by removing either say the MLP neuron or attention heads completely, it could like disturbs the computational graph. And also the fine-tuning process of such a compressed model, they don't really follow the same optimization trajectory compared to the dense model. And also because the pruning process will be relied on this calibration data that we say for NIRVANA, we collected gradients based on this small batch of data. So if the distribution of the data shifts in the future, that can make the process highly sensitive. And also because for an LM, attention and MLP, they typically plays different role in the process. So by not balancing the effect of these components can also result in suboptimal performance. And building on that, the goal of NIRVANA is to first preserve the model's zero-shot accuracy and also try to maintain the fine-tuning recoverability. This is the overview of our method. So we first start, similar to other unstructured pruning method, we have this saliency score, which is the score that we say calculated for each weight in the model. And then we use this score to rank all the weights to do sort of like determine their importance for the model. And then we bridge this to neural tangent kernel, and to show that by using our saliency score, we are able to preserve the NTK during the whole process. And then connecting this to the structured like level, we group those unstructured score by either the MLP neuron or the attention head. And um, sorry, I just saw the poll question, and yeah. Then for the model level, now we have like say the all scores across different layers and components. We now like rank them jointly. Say like for local pruning, typically each layer in the model will have the same sparsity level, but it's not typically the case for LLM, because say like the input or the output layer, they might have higher sensibility compared to the middle layer of the model. So by providing this flexibility across all layers, and also balancing between the MLP component and attention component, we are able to provide a more flexible and then stable results compared to, say, like local pruning. So yeah, and then like we also have this calibration data selection process following the pruning, like score calculation. So first, for the NDK-guided saliency score, we start with a first-order Taylor approximation, which is essentially like measuring the effect of removing a specific weight in the model. And that gives us the base saliency score, which is like the magnitude of this effect of like how large the model's output will change after we remove that specific weight. And then we connecting the saliency score through a theoretical tool of neural tangent kernel. So basically, NTK describes how the model's prediction will change or evolve during training. So if the pruning can effectively preserve NTK during the process, we could show that they follow a similar optimization trajectory compared to the dense model. Hence, the fine-tuning recovery will be more stable. Then like under Adam, the optimizer Adam, the NTK spectrum is essentially as the following form. So the observation, which is like essentially for a single weight, it is just like the first term of our saliency score. And we add this like weight here also, to balance like not only that the weights effect of the gradients change, but also for like the how large that part is. And by providing a theoretical proposition, we proved that using our saliency score, we could ensure the NTK stability during the process. And then we group our like weights together for MLP neurons and attention heads. For example, for MLP neurons, we add up every like input connections and also output connections for that specific neuron. Then we use the adaptive sparsity allocation through a ratio gamma, because we observed that MLP attention, they're not equally important and also resilient during the pruning process. So we theoretically derived a value for each model we pruned. And we also provide some empirical evidence that the MLP neuron and also the attention has, they are like not equally important during the process. So the first one is the perplexity result of NIRVANA under the sparsity ratio, I don't know, like control of gamma. We could find that you see like it's actually smoother than simply doing pruning on MLP neuron and also for attention head. And we could also see that the tension had actually collapsed just at a very moderate sparsity level. And then for the calibration data selection process, the previous work, they typically just randomly sample data from, say, either C4 or Wikitext, and that it doesn't really consider how the data's role during this process. Because as previously mentioned, the actual data your test model can shift during the process. So if the calibration data you use to calculate the score is different than the actual data the model is used, that can potentially impair the model's generalizability. So we use a anchor set to measure like the KO divergence between the prune model and also the original model. And then we select the calibration data batch, which results in the smallest KO divergence, which is like essentially like say best preserve the model's output after pruning. And then we provide like we could see this small set as a Monte Carlo estimator. So the average KO divergence on a small center anchor batch V can be seen as an unbiased estimator of the actual expected divergence. And then we also proved this using some empirical evidence. We could see that there is a clear correlation between the KO divergence on this small set and also the real world like perplexity performance. And we also do a hardware alignment step on this process. This is because like even if reduce the parameters or like units in the model, they don't really like typically not really give real speed ups if the dimension of the resulted model is say not a multiples of 8. This is the experimental result of NIRVANA. So we tested both the zero-shot accuracy and also with the slightly LoRa-based recovery fine-tuning, which takes like under 2 hours to help the model recover some process. And we found that both on zero-shot accuracy and also on the recovery test, NIRVANA is able to like reach the state-of-the-art results. And this is not only on like say easier tasks like Winograd or HellaSwag, which is like multiple choice, where the model just need to say like evaluate what the like the higher probability throughout the options, but also for like harder task like MBPP, which is a coding task. In that task, the model is actually need to generate the code and then like should be like make sure the code is runnable and also like no grammar errors. So those like harder tasks, NIRVANA can retrieve better results, demonstrate that we're not only just able to say preserve some more like easier knowledge, but also say for the deep reasoning circuits during the process. And we also have some efficiency results. Say like we found that for previous method, like even if they are able to reduce the memory cost, the throughputs can even be worse than the dense model. So this is because they don't do this alignment process during pruning, and then the result that like the dimension of the model could be like even not even an even number. So that makes the latency of the model like even worse. And like instead, because we add this hardware aware alignment, the improvement is monotic and then like can reach up to 60% throughputs improvement. And then we also do this ablation study because NIRVANA has like say several core components, and we found that removing any of them will have like large drops in the performance. So some discussion like why NIRVANA might be working is first that we not only like just derive our saliency score, but we also connect the score with the NTK theory to make sure that the model not only just perform better during the zero shot, but also during some recovery fine-tuning process, the model can have, say, the trajectory of the optimization can better align with the original model. And then we have the KO selection process, which makes sure that the data we used can better reflect the real world data the model is tested on. And also we balance the effect of the MLP versus attention and also like different layers. But we also have some limitations. So first, when calculating the saliency score, because we are using the gradient in the process, we do require a backward to collect the gradients. So it can be slower compared to a simple magnitude pruning, which you only need to evaluate like how large that weight is. But this is like pretty effective. Say it takes only seconds to complete. And also because we have this KO selection process, which actually need search using like on different batches, that could also add overhead to the process. But because we're like, we like typically use a very small batch of data to do this. So that search process can be finished under 10 seconds for each step. And because we are also assume that the recovery is using Atom, if the model, say, is trained with SGD, the form of the saliency score could be different because for SGD, the NTK will have a L2 norm compared to the L1 norm that we're currently using. So in conclusion, we propose NIRVANA, a structure pruning method, which is theoretically grounded and also a like practically effective solution during the process. And thank you for your attention. I'm now happy to take any questions.
Yeah, thank you for your presentation. And I think we have a lot of time for questions. If anyone has questions. I think not yet. Yeah, I actually didn't understand the part about the calibration data. If we could go back there. Yeah, so I'm not familiar with pruning literature. So by calibration data, do you mean the data that we use to for the like for finding the weights that need to be pruned away, or?
Yeah, so typically in pruning, when we calculated, say, like our scaling saliency score of, sorry, like this, right? We do require like the gradients in the process. So in order to get the gradients of the model, we will have to use like a small set of data to actually calculate and collect that. So that is what calibration data means, like the role of calibration data through the process to say like serve as a say like proxy or anchor to like so like so the model can collect the gradient to reflect its features during process.
All right, so this calibration data has to be sort of from the same distribution from which you on which you eventually want to use the model.
Not really, because we specifically designed this to be task agnostic. So like here, when we test the model, the perplexity, we test on Wikitext on the PDB, but to make sure that it's actually zero shot, right? So we drove the calibration data from another data set, book corpus, to make sure that there's no overlapping between the data that the model is tested on and also the data we use during the process.
All right. Yeah, I think I understand. Thank you.
Yeah, of course.
Do we have more questions from the attendees or from one of the panelists?
I wish to quickly also mention that you can also use Slack to post questions. I posted the link to Slack invitation on this poll thing. I tried this for the first time. I hope it works. I also have one question here. So you're using neural tangent kernel for determining the important kind of weights of the model. And you mentioned neural tangent kernel is kind of keeping important information for the training dynamics. The reason why we want to use that is because this is designed for fine-tuning stage. All right. So during fine-tuning, you probably want to have more information about the training history or the training status of the model. And if we do not make use of the gradient direction, for example, then we do not have the right information for doing further fine-tuning based on this model. Is that right?
Yeah, exactly. So so the first, like when we derive the saliency score, it's just like at first it's just a simple first order approximation, which is like pretty common to the previous pruning work to use this first order information. But then like we found that we could actually connect this with neurotangent kernel. And also for previous work, I think most of them, when they're calculating gradients, they use the gradients with respect to loss. But here, because we are viewing this in the neurotangent kernel, we're actually doing the gradient with respect to the output. And that enables us to connect our saliency score through neurotangent kernel. With this theoretical tool, we can find that during the fine-tuning process, like when the model is evolved during training, the trajectory of the optimization can better align with the say the original dense model.
I think this is super cool kind of observation. Do you also think, so I can imagine there can be kind of pruning that's designed for fine tuning, as well as pruning that's just designed for inference, like faster inference. Do you think actually this NTK based method could also help with just inference specific kind of pruning as well? In other words, do you think compared to other kind of methods that are designed for inference time, do you think this neurotangent kernel method can also benefit?
Yeah, so like from the experimental result, we not only test the say with the recovery results, right? We also have the zero shot result where the model just like we test the model after we perform this one shot pruning process. So we found that not only like after some small recovery training, the model can have better performance, but also for zero shot performance, it can, results in like better performance compared to the other method that is specifically designed for inference. So it might also like contribute to other components, say like gamma and also the calibration data. But we believe that the NTK score probably also plays an important role in the process because of, say, the first order Taylor explanation that, you're just trying to minimize the model's output, right?
Yeah, this is super cool. I missed this result here. So you also mentioned this calibration data selection. Is this something kind of new? I hate to ask this question, but I also don't have much information about what's the current landscape of this pruning research. So can you explain a little bit how novel this is?
So typically for other pruning methods, like say like some famous one like SparseGPT or one that when they when they collect the gradients, they just randomly sample data from their large set, and they don't really evaluate how sensitive of the model's performance after with different batches. Well, that makes sense because for unstructured pruning, the performance is comparably stable to the data that you're choosing. But for structured pruning, because now you're removing like the entire attention heads, the model become more sensitive, and the information stored in the model could be like easier to lose the model's information by using different data. So there are some recent works, say, for example, I think from iClear last year, iClear like 2025, there is a work about like use the model to generate the calibration data for itself. We also tested that method. Actually, it didn't really work as expected. It probably because like in their experiment, they use larger models, say like Llama 70 billion. So the data from the model can probably have better quality than a smaller model, the 8 billion we're using. So we connected this with KO divergence because this is more like a direct connection between the prune model's performance versus the original one, not just like because there are previous work to investigate this effect, like how many examples you're using from the data, and also how long the data, the sequence length, or just like if the data has better quality, say maybe has some in context samples like question answer, whether if those effects that human can understand might have contributed to result. But during our experiment, we found that they're more heuristic. So it's just like by connecting the output directly through the KO divergence might be a more effective approach, because we are essentially let the models like we observe the performance based on how model prefers data using this calibration batch.
Thanks. Overall, I think this is quite interesting. Yeah.
Yeah, thank you. So I guess I'll hand it to Ankit.
Right. Thank you. So I think, yeah, I'm gonna share my screen so that, yeah, you can see the intro and stuff. And yeah, let's try this. I think it works. Can you see my screen?
Yeah.
All right.
Okay. So I think John is also like an author from the paper, right?
Yes.
So
That is
yeah,
correct.
so Ankit is a PhD student from I don't really know how to pronounce Germany, but I think it's from University Tübingen. Correct me if I'm wrong, but and he's going to present their work about the rankability of visual embeddings.
All right. Thank you for the introduction. And yeah, I forgot to mention actually my. Okay, I did mention it in the header, but I forgot to mention it in the main slide. But yeah, yeah. So I'm gonna present our work on the rankability of visual embeddings that we're also gonna present next week at NeurIPS. And yeah, so Before we talk about the paper, I just want to spend a few minutes going over the background. So our work is part of a broader, like kind of huge body of work that tries to understand the geometry of VLM embedding spaces in order to understand what kind of information they contain. So what does that mean? So it simply means that if you have a set of images in raw pixel space and you pass them through an image encoder, let's say Eclipse image encoder, then the model has now compressed that data into a lower dimensional embedding space, and you want to understand how what the model thinks about how this data is structured. Does it kind of structure the data in a meaningful way so that, let's say, dog images are put together and then cat and horse images are kind of far apart from dog images, but then all animals are kind of put together and food items are in a separate cluster and people are in a separate cluster. And yeah, maybe the data is organized less regularly from a human's perspective. Maybe it's just organized in this random manner where, yeah, random things seem to go together and we don't know why that happens. Um, and this kind of structure diagnosis lets us answer questions like, yeah, like I said, like does Clip know that all dog images are similar in some sense, and whether all animals are similar to each other? Does Clip know that a concept like age exists and that people can be arranged based on how old they are? And yeah, whether classes are linearly separable and so on. So, yeah. And in our work, we are concerned with ordinal structure. Now, what does that mean? So it means, let's say you have a set of images and there is some sort of ordering that you can do on top of these images. So you can say that, yeah, that people can be arranged based on how old they are, and to every image you can assign this number that tells you how old the person is. And yeah, this way you can arrange the images so that there is a clear ordering. In another instance, you can have set of images where you have a lot of people in one image, and it could be different people, different amounts of different numbers of people in different images, and you can arrange your images in that order if you like, if Clip's embedding space has that kind of information. So really, we're concerned with the global structure of the embedding space, and this is different from retrieval, where we are more concerned with local structure as to whether the the top like 4 or 5 neighbors of a given query, in fact, do correspond to the samples that you would expect to find there. But yeah, we are more concerned with whether Clip is aware of this kind of global structure that emerges if you arrange the images by some semantic concept. And yeah, there are many such concepts, and I showed you 2 here, and we'll look at more. And yeah, so we look at these ordinal attributes, and then we define rankability as simply how much the VLM in question. We mostly talk about Clip here, so how much Clip is aware of such ordinal attributes. And yeah, good rankability. So good awareness of such ordinal attributes would also mean that if you construct a vector database out of these images, then you would have the ability to quickly organize your images in a manner that probably makes sense to you. So that would be a nice application. But in general, I think that if clip-like models are to be used in modern, even let's say like as a vision backbone in some generative VLM, it's always good to have this kind of ordinary information, and it can maybe better answer questions that require this kind of information. So is this property obvious to have, and does it make sense to study whether VLMs have rankability? Well, we think not, because if you look at the, let's say, the training objective of CLIP, it does not say anywhere that for example, like images of more like highly crowded images should be closer to crowds of like, let's say, middle-sized crowd, or however you say it, as opposed to how close they would be to very sparsely crowded images. So yeah, I hope it makes sense that this property is not obvious. Uh, but still, if it's not obvious, then why do we even try to see if it exists? Well, that's because many properties are emergent, and we should try to look at what's happening in modern systems before we try to push for further improvements, basically. So yeah. Before we move on, some definitions. Um, Visual embeddings are simply in our work, they are simply the final layer output of a visual encoder just before we attach the downstream model. So for a vision transformer, it's just the CLS token, or for a ResNet, it can be the layer after global average pooling. Rankability with respect to a given attribute is simply if you were to find an optimal linear projection over the embeddings, then how well is that projection respecting the ground truth ordering according to that attribute? And why do we use linear? Well, it's partly to be consistent with prior work on topics like linear representation hypothesis. And yeah, linearity is just simply nicer, and it's if you have linearity in your model, then it also becomes very easy to extract this kind of information, and it's overall better for your applications. Right, so just a technical definition. I think I already kind of went through the high-level definition of rankability. We can come back to it if there are questions. Now we look at the attributes that we use. So we use 7 in total. We've got age and crowd count and some face pose angles. So these are called pitch, yaw, and roll in face pose terminology. Then we've got image quality and image modernness. So it's a measure of how recently an image was taken, and yeah, this used to be kind of discernible for images in the past. All right, so and we use both clip and non-clip models. So we try to have a good mix of architectures here. So we've got ResNet, VIT, and CondNext vanilla versions, and then we've also got the clip versions of these models. And yeah, and they've got parameter counts ranging from 25 million to almost 200 millions. And yeah, and then how do we measure rankability? It's actually quite straightforward. So we've just got a data set that has these labels. So each image gets a number. That number denotes the value of the attribute of interest. And we train a linear regressor that tries to predict that number. And yeah, we just use mean squared error loss in our case, but in principle, you could also use something more sophisticated like hinge loss. Let's say if you have pairwise comparison data instead of actual numbers. And then over the test set, we just measure the Spearman's rank correlation coefficient, and naturally a higher SRCC would mean better rankability. Right. So it's one thing to calculate the SRCC, but it's another thing to also tell if the SRCC we get is actually worthwhile, if it's actually a good indicator of rankability. So there are some prior works that also try to tackle these ordinal regression questions, and we do look at them to like compare our results overall, but we also construct some other baselines of our own, one of which is this randomly initialized encoder. So we just take an encoder that we are trying to test, and yeah, we randomize all the weights, and we see how good is the embedding space of this um, like random, basically this random embedding space already. And yeah, we thought that this would be a good baseline to compare to. Then the second one is just our main rankability measure that we present in the paper, and then we've got two more measures. The first one is the information content of the encoder. That just means that if you train nonlinear MLP over the embeddings, then how much better do you perform compared to the second case, where your embeddings, where your sorry, 1 second, I pressed some keys. Yeah, so basically, you train a two-layer linear MLP, nonlinear MLP, which is supposed to be a universal approximator. So it will extract all the information that's present in your encoder, and that way you can tell if your linear regression was good enough to indeed extract all the information that was in your encoder. And the last upper baseline would be if you were to unfreeze the vision encoder as well, and you were to optimize simply directly for your task of interest.
Quick time
So
check.
yeah. Sorry?
It's a quick time check. You're supposed to use 50 minutes, ideally.
Yes, sorry. But I think it's been about 10 minutes, right? Or did I take longer?
I think it's fine to just speak a bit more. I mean, I'm not saying you should stop now. I'm just saying, oh, please watch the time. Yeah.
Thanks. Yeah, I'll try to speed up though. Actually, I'm kind of done. So we've got I hope the baselines were clear. And then we move to the findings. So the first finding is this qualitative. So if we look at CLIP's embedding space, qualitative examples in CLIP's embedding space, we see that it does kind of arrange images in the order that you would expect. So I'm showing examples from 4 data sets here. And as you can see, in all cases, the ordering over the ordinal labels matches what you would expect from like the ground truth labels. Then we also look at quantitative measure. So as we can see in most cases, the second column rankability measure is more or less very close to the fine-tuned upper bound, On the other hand, random embeddings did not perform very well as expected, but yeah, that was also supposed to be just the lowest baseline to contextualize our rankability measure. Right. Yeah, and that text just says what I just told you. So yeah, we find that models are pretty rankable when compared to baselines. And yeah, rankability kind of varies across attributes as well. In the interest of time, I'm kind of gonna skip over that part. And yeah, we also find that clip models are better than non-clip models. So it kind of hints towards this hypothesis that language supervision leads to such emergent properties like ordinal information awareness. But we don't make any broad claims here because the experiments can also have other confounders like the size of the pre-trained data set, which is usually higher, much higher for clip models. So yeah, and the other finding was that it's usually enough to find just a few samples for obtaining these rank axes, and sometimes it even suffices to find just a difference between two images that lie at extreme ends of the rank axis. And yeah, that was our observation about sample efficiency. And although that was not our main observation, so I'm kind of going to skip over that as well. Um, yeah, to conclude, we try to study this new property of rankability for visual embeddings. And actually, when we started out, we were expecting that they would not perform as good as they did. But yeah, our observation was that clip-like models do in fact show pretty good rankability, and that these rank axes are also easy to find. And we expect implications for understanding as well as for practical applications like vector database sorting that I mentioned earlier. And that also brings me to the close of my presentation. So thank you for your attention. And yeah, so actually next week we are going to be presenting our work on two continents. So yeah, please feel free to come by or send us a message later on. Thank you.
Yeah, so first, congratulations to your acceptance of this favorite universe. And then I have so it's actually like pretty interesting that if you know look at this in a higher level that the
Mhm.
visual embeddings that can be rank through approaches. Like what do you think might be the like cause of this? Does the model like through the embedding they actually understand how the images represent? Like what's your observation on this? Like, yeah.
So you're asking if the model actually understands ordinality.
Yeah, yeah, sort of like that, just like I'm trying to understand like why this could be, um,
Mm-hmm. Yeah, we had many kinds of conjectures that don't apply to all models at once. So for clip models or language guided models in general, we had this hypothesis that label noise is actually responsible for this kind of information emerging. So so for example, like if somebody is 20 years old, then the annotator might, or in this case, just caption, but caption might mention that person as 18 or maybe 22 or something, but it wouldn't mention, for example, 40. At the same time, someone who is 40 years old would be labeled as maybe 35 or 45 or within that range. And we thought that this kind of label noise is resulting in this natural ordering where 40-year-olds are close to 35-year-olds, but 35-year-olds are then closer to 30-year-olds as opposed to 50-year-olds, if that makes sense.
Mm-hmm. Yeah, and also for the sample efficiency, I think page 13.
Yes.
Right. Yeah,
Yes.
actually, like I know you mentioned this is like not a major find of this work, but I actually do find it's pretty interesting to see that so if you just take two images, two samples that have like the largest distance to the process, like the model can perform pretty well. Like probably maybe like and there's some differences between those two video embeddings, and then by finding like in what axis the like the difference can be most extreme. Like you can actually learn, the features from this. This is actually, I think, a yeah, pretty interesting finding, and maybe like demonstrate something that like probably like say the geometry of the ranking could potentially be like low dimension, like have you tried like maybe just using PCA to see like whether those matrices are low rank? Just sort of like that. It might not be true, just like, my gut feeling.
Yeah, now that you mention it, yeah, we at some point we might have discussed the dimensionality of the ranking information, but yeah, I don't think we actually did PCA. Although, yeah, now that you mention it, this could be a whole new research question in itself. So yeah, maybe I'll look at it at some point. But,
Mhm.
yeah,
Yeah, of
thank you for
course.
the question.
And because like someone in my lab, they also did some research on VLM reasoning recently. And I also find like it's kind of related that when you're trying to understand not just for language model, but for like those things specifically for VLM, that it requires, say, like collaborations between the visual, embedding, and also the language part, that like sometimes when the model is trying to locate the information required for reasoning, like what is the dynamic during like the model that could be, shifted to the process. And I think like to understand that through the rankability is also a pretty like good lens through this, because um yeah, because like if the images can be ranked, say like ages or like crowded, right? There must be some features in the embeddings that actually capture the thing. So yeah, like overall, like really cool paper, and really like your work, and I definitely check more. So yeah, I really like the idea, and then like I think it's pretty good contribution to especially like the explainability of VOM. So thank you for your presentation.
Thank you. Yeah, I hope that yeah, that the community finds it interesting. Yeah, it was really nice to have your questions. And yeah, I'm gonna look at the dimensionality question more. And now that you mention it, it would be kind of interesting to see if whether this kind of information being low
Hmm.
dimensional would help the visual, the language part to like reason about it better, or
Hmm.
yeah, it may be like, yeah, in context of what you mentioned about the related work from your lab. Yeah, it would be kind of interesting to check that.
Yeah, exactly. Thank you so much for your presentation.
Thank you.
I have a follow-up question. So can you maybe share the related work from your lab, maybe later?
Yeah, of course. I'll
That'd be
of
great.
course.
Yeah.
Um, and on top of that, I'm also like, now that you mentioned the language part, I'm wondering, Ankit, what do you think about the language domain? Do you think you're going to see like a similar structure, like ordinal structure in language embeddings as well?
I think it's more likely to to immerse in language. This language is already very structured. Yeah, so are you thinking of Clip's text encoder?
I was thinking more of BERT embeddings, for example, or BERT embeddings, or typical embeddings that people use for information retrieval.
Yeah, it looks like it would emerge, but we don't know until we check.
I mean, maybe they contain all the kind of nice properties that you mentioned, like noisy labels, or kind of targets, which are kind of encouraging the samples to arrange in a more regular manner, I guess.
Yeah, it could be. Yeah, the other thing, I would be curious if that information exists, then is it lower dimensional than the vision counterpart? Yes, it looks like it could be. Yeah, although I'm not sure. Yeah, it would be kind of hard to test because for language, like how many different kinds of samples can you have? So I guess, yeah, something to think about.
Okay, cool. So thank you. Unless there's any other question from the audience, or okay. Then thank you for great thanks to the speakers today, Ankit and Mengting, for presenting your work, especially Mengting joining. Now I think it should be 2 a.m. in the morning, right?
Yeah, I probably need to jump into bed right after this.
Yeah, thanks a lot for still joining and making such a nice session with us. Thank you again, and we can probably get started or for the preparation for the next session then. Thank you again.